We've been talking about pi-CC bonds acting as nucleophiles for carbon-carbon bond-forming reactions. And we introduced the idea that the Prins reaction, the addition of alkenes to carbonyl groups, is a powerful way to think about modern organic synthesis and the formation of carbon-carbon bonds. So when we left off, we were talking about not just regular carbon-carbon double bonds, but we were talking about the use of allylsilanes, alkenes with these long bonds at the allylic position, carbon-silicon, carbon-tin, in order to soup up the nucleophilicity of the double bond. And if you use Lewis acids or some sort of an acidic species, we could generate something that looks very much like an aldehyde or a protonated carbonyl that could then add to these souped up alkene double bonds. So we showed this example of a Prins reaction to cyclize to make a 5-membered ring. Now, you don't have to start with an acetal in these reactions. You can make an acetal-like derivative in situ by simply adding an aldehyde and an acid. So here's an example down below where they've used trifluoroacetic acid to catalyze hemiacetal formation from an alcohol starting material and an aldehyde starting material. And I'm not going to draw all the steps in the acetal reaction, but you'll generate an oxonium ion intermediate that looks very much like a protonated carbonyl compound, this group right here. And so now this CC double bond, this allylsilane next door, will add into that and then form this new CC bond in this ring. Now, you can get a little bit trickier than this. We don't really have to make any kind of an acetal intermediate. Really, all we want is this thing that looks like a protonated aldehyde. And instead of using protons, it's very common in modern organic synthesis to use Lewis acids that love oxygen, like titanium would be one example. Tin 4, not stannous dichloride, but stannic tetrachloride is a oxophilic Lewis acid. Boron trifluoride, we've already seen in some of our problem sets and in lectures, acting as a Lewis acid that really loves to form bonds to oxygen and then come off so that it's catalytic. Scandium is a more modern Lewis acid used for Lewis acid catalysis. As long as you have triflates on there, those triflates will exchange very readily, so other oxygen atoms can attack and then the triflate can come off. So let's go ahead and take a look at a mechanism for how you can use this combination of an aldehyde and a Lewis acid in order to generate electrophiles that allylsilanes can add to. So here we're using the lone pairs on this oxygen carbonyl to come down and add, or to come over and add to that titanium. And in the process of doing that, we generate an oxonium ion, looks a lot like a protonated carbonyl, and this titanate intermediate, and that's electrophilic on that carbonyl carbon. So now if you have an allylsilane in there, it should be no surprise that that allylsilane can come in and add in order to generate a CC bond. Now we've got to find some way to draw the mechanism where this chloride will come off of the titanium and help us displace that silicon in order to regenerate a double bond. So initially it's very difficult for a chloride this chloride to come off because there's an O+ next door. But once we add that allylsilane in, now there's a lone pair available on the neutral oxygen that can accelerate the rate at which that chloride comes out as a leaving group. And I'm not going to start my arrows with the oxygen lone pair, but I'm simply going to show that the chloride anion can come out of the titanate anion. And that leaves us with a chloride anion, and I've drawn that down below the silicon because I know that we need to get the silicon off, and we need a nucleophile to help make that happen. So I'll go ahead and show the chloride anion adding to the silicon. That makes this siliconate intermediate, and that siliconate is now ready to give its electrons to that carbenium ion in order to reform the CC double bond. So eventually this silicon wants to end up attached to oxygen, and we've generated this very reactive trimethylsilyl chloride intermediate. So we've seen these types of processes before where you silylate oxygen, alcohols usually, with trimethylsilyl chloride, and this is even better when it's an O metal bond, kind of like O sodium or O potassium. We have titanium on here, So we add to the silicon and make a pentacoordinate siliconate intermediate, and then in a second step, the chloride comes out. So now we've got this great looking silicon-oxygen bond and this chloride ion sitting around. Right? The chloride can come back and attack the silicon. That's certainly happening, but it's not interesting. Let's go ahead and draw how we get the titanium off. We'll attack the titanium, and now that makes it very easy for us to break this bond here. And I find that sometimes people are unsure about how to break a bond when you've got two different looking atoms there, but here it should be an easy decision. We've got O+, and oxygen does not like to be positively charged. So let's go ahead and use that bond and give the electrons to the oxygen so it ends up being a neutral oxygen. And that regenerates our titanium tetrachloride catalyst in this reaction. Okay, so allylsilanes can add to aldehydes as long as we put in either a protic acid or a Lewis acid. So why wouldn't you want to put a protic acid in here? Well, you don't want to proto-desylate it off your silicon, right? It's very easy to protonate allylsilanes, so you wouldn't want to just throw in, acids every time. You oftentimes get better results using Lewis acids and keeping the protons out of the system. Okay, so we've been talking about long bonds, allylsilanes, allylstananes, ways to make that double bond more nucleophilic. But let's come back to second row atoms. So when you have alloboron compounds, if this were just an alloborane with a neutral B, that wouldn't have any special nucleophilicity. But if you make it a boronate with a negative charge on boron, now the bonds become nucleophilic. And this nucleophilic carbon-boron bond here is donating into this pi system and making that pi bond more nucleophilic. So you can see in this reaction they're starting off with an acetal, and they've got not a Lewis acid but silicon, which can help pull off that one of those two methoxy groups. And now instead of using an allylsilane, we're using an allyl-boronate compound. Let's go ahead and draw out the mechanism for that process. We've already seen an example where TMS triflate can act as a silylating agent. Boy, silicon loves to be attached to oxygen. It just doesn't love to be attached to a triflate oxygen. Nothing wants to be attached to a triflate oxygen. Triflate is one of the best leaving groups we have. So let's go ahead and draw out that substitution process. I'm not going to draw out both steps of that process, but I will draw the first step. So here's our silicon. And we've got this triflate leaving group on there that's very powerful. Makes it very easy for either one of those two methoxy lone pairs to attack the silicon. And there's a two-step substitution process. I'm not going to draw both of those steps, but I will draw the intermediate after we've transferred the silo group. And so now that turns one of these methoxy groups into an oxonium. And it's got this really great-looking silicon-oxygen bond there. And the lone pairs on this other oxygen were just waiting for a chance to push out its neighbor. So very easy for the other lone pair on the other oxygen to push out this trimethyl silyl ether as a byproduct in the reaction. And so this generates an oxonium ion. Just looks a lot like a protonated carbonyl group, except now it's got a methyl group on there. And so it's very easy for nucleophiles like alloboronates or allylsilanes to attack that oxonium species, that carbonyl carbon atom. So let me go ahead and draw out that alloboronate species. So I'll go ahead and depict that with this B- bond there, that negative charge on the boron. Let me circle it so we can really see that. Makes that pi bond more nucleophilic. And I'll draw the mechanism here. So the boron, the carbon-carbon double bond adds and then leaves behind a carbenium ion that's highly stabilized. In this case, you might debate whether you're simultaneously breaking the carbon-boron bond, or do you actually go through this. I would accept either of those mechanisms in this class. Right, do you go through this carbenium intermediate and in a second step break the carbon-boron bond, or do you use the carbon-boron bond while you're using the alkene? Either one of those would be acceptable to me. We'll see cases where we're quite sure, because it's paracyclic, that all of those bond changes are concerted. So alloboronates are very nucleophilic, just like allylsilanes. Now let's move try to combine this together. It's like you can get these very fast reactions with allylboronates and these oxonium-ion species, and they're so reactive they go at -78. But the problem with this is we had to synthesize both of these starting materials. So like, where do you get this acetal from? Well, you make acetals from aldehydes. So somebody had to synthesize this acetal from an aldehyde. And where do you get boronates like this from? Well, you have to add an alkylithium or some sort of a Grignard reagent to a boron compound. So you had to synthesize this from an alloboron compound, and you had to synthesize the acetal from an aldehyde. And some clever person realized, well, why don't I just throw those two starting materials together, and maybe I can get the same thing to happen in my reaction mixture. And this is the way we do modern organic synthesis, right? The lone pairs on the carbonyl will add to boron, just like they can add to a Lewis acid or BF3 or some other species. And when you do that, boy, you end up with this magical combination here. Let's go ahead and draw out this next intermediate, because it is perfectly set up for a very rapid carbon-carbon bond forming reaction. So now, with the Lewis acid attached to the carbonyl, we have that really soups up the reactivity of the carbonyl group. And at the same time, we turn the neutral boron into a boronate. And that means this bond right here is more nucleophilic and is increasing the nucleophilicity of the CC double bond. So you can't stop this now souped up CC double bond from adding to the carbonyl. And at the same time, this carbon-boron bond will be donating into that pi system in order to break the boron-carbon bond. And so these reactions are so facile. They go at -78 degrees just by putting these things together. So you'd have to cool this down to prevent it from overheating. And the magic behind this type of a reaction is not just that you don't have to synthesize a bunch of starting materials. It's also that the stereoselectivity of these reactions is highly predictable, because they go through a six-member transition state like this. It's not just a six-member transition state, but it goes through a chair-like transition state. So in the transition state, you're forming a new bond between that carbonyl type carbon and the end of that allyl system. And if you have a substituent on here, let me draw a substituent here, and that substituent is going to be, you could have it either cis or trans to this other carbon-carbon bond. I'm drawing, in this particular case, if it's trans. If it starts off trans to this double-double bond, that means in the transition state, it's going to be trans to that carbon-carbon double bond. This bond will be anti-paraplanar because it was anti-paraplanar in the starting material. Once you know that, all you have to do is draw a chair where the substituents are at equatorial positions. And where do you get to choose that? Right here. The aldehyde can add where the R group is up or the R group is equatorial. And it prefers for the R group to be equatorial in a chair-like transition state. The stereoselectivity in these reactions is highly predictable simply by being able to draw good chair conformations. And this is the way we do modern organic synthesis. Things that look like alloboranes adding to aldehydes, that represents a lot of the way we assemble carbon-carbon bonds in modern organic chemistry. All right. Wow, beta-silyl carbenium ions. So long bonds. Let's come back to this idea of long bonds. So I want to contrast two similar sounding but very different reactive species here. I want to contrast the two functional groups, one called a vinylsilane, and contrast it with an allylsilane. And so here I've drawn two different propene groups attached to silicon. And so this group over here, that I would call an allylsilane. So that's an allylsilane. It's an allyl group attached to a silicon. Over here, it's an alkene. Whoa. Over here, when the screen comes back, over here, we would call this, you could call it an alkenylsilane. But quite often we use this much older archaic term. I still use this older archaic term. I think most chemists do. Instead of calling it an alkene, we call it a vinyl group. So alkene and vinyl. You might have seen white plastic pipes called PVC, polyvinyl chloride, vinyl. Maybe if you're taking the materials class, you might call some of your monomers vinyl. monomers. Sorry about this, the screen going out here. So these have the same molecular formula, and what's amazing is that they both, in theory, have the ability to form the same beta-silocarbocation. So if I draw protonation of this allylsilane right here, right, I would protonate the end of this carbon-carbon double bond. I would protonate the end right there. Let me go ahead and draw out my arrow pushing. And that would lead to this beta-silocarbocation. Awesome. We've been doing that all quarter, making beta-silocarbocations. This is usually a side reaction. Nobody would purposely protonate a beta-allylsilane, because you usually use those for CC bond formation. But if we took this isomeric vinylsilane over here, where is this thing nucleophilic at? We had a problem on one of our problem sets where we talked about this, and what we said is you want to protonate next to the silicon on a vinylsilane. Next to the silicon. Why is that? Let's go ahead and draw that out. Well, the reason why you want to do that is because if you protonate next to the silicon, right, when we do that, we end up with the same beta-silocarbocation. If you protonated over here, you would end up with an alpha-silocarbocation. Those aren't stable. We've never talked about alpha-silocarbocations. That's not the end of discussion for that. So really, you get both of these will lead to the same beta-silocarbocation, and the only difference is whether we put the proton next to the silicon or farther away, but it's the same beta-silocarbocation. What is not so obvious at first sight here is that the allylsilanes, oh my gosh, what the heck? Holy, okay, let me just fix this. I've reversed the words here. Allylsilanes react much, much faster. God, that's insane that I would write that there. Okay. And vinylsilanes react slower. Allylsilanes, we do everything with allylsilanes. Vinylsilanes you can use sometimes, but they won't be fast like the allylsilanes are. So let's go ahead and talk about why that is. Right? If the rate is just based on which carbocation you form, haven't we been using the stability of carbocations to predict how fast reactions are? Right? If it forms the same beta-silocarbocation, it ought to be equally fast. But that's not true. I want to go ahead and draw out the interaction of an allylsilane, the interaction of the silicon with the pi star system, so we can help to think about that. I'm going to try to sketch out here a picture of what does this orbital, what does this look like when you add to pi star? When this long silicon carbon bond with its electrons, I'll just shade that down here, adds to pi star, right? It donates in, and it makes, as you interact with this long carbon silicon bond with that pi star orbital, as you donate in, you create a new orbital that's higher in energy, a new pi-like orbital that's higher in energy, and it is nucleophilic on the opposite face. The orbital would be bigger there in that new orbital. So we've already talked about this facial preference when you have allylsilanes. It's that carbon-silicon bond interacting with pi star that makes the alkene more nucleophilic. But now let's come over and draw a similar situation here with that alkene. Right? If I draw that pi star orbital here for the alkene, when it's a vinylsilane, I don't have this good interaction anymore. It doesn't matter how I phase this carbon-silicon bond here. Whether if I phase it hashed, it'll have a good interaction with the bottom part of pi star, but a destructive interaction with the top. Or if I phase this so it's unfilled, if I phase this carbon-silicon bond so it's unfilled, now it's got a bad interaction with the bottom and a good you get zero interaction, net interaction, when the carbon-silicon bond is sticking off the side of the alkene. That carbon-silicon bond is doing nothing to the nucleophilicity of that alkene, like nothing like that allylsilane. So the problem with vinylsilanes is at the beginning of the reaction, that carbon-silicon bond is orthogonal to pi and pi star. It's not affecting the nucleophilicity in the same way. So, but there is a slight effect. And so let's go ahead and talk about what happens as we add an electrophile. And just for the sake of simplicity, I'm going to take a dumb electrophile like a proton. Again, nobody purposely protonates off their silicon groups. You want to use vinylsilanes and allylsilanes for CC bond formation, not just popping them off the silicon using a proton. But if you did add an electrophile, bromine, iodine, carbocations, then you would expect that this CC double bond would attack, and where would that CC double bond be nucleophilic at? It's the carbon next to the silicon. We already said that. So as we add our electrophile here, there we go. As we add our electrophile, we're going to protonate right next to the silicon. And as we protonate right next to the silicon, I'm going to do my best job here to start off by drawing the alkene in the same place. I'm just not going to draw the double bond. But as we add that proton, it's going to pyramidalize. So if we add that H from the top, now that silicon is dipping a little bit below the plane of this carbenium ion. So now it's not perfectly orthogonal anymore. The silicon is now, because this is pyramidal, this silicon is starting to go below the plane of the board. And there will be this rotation that will occur. This silicon is starting to feel like, oh wait, I'm on the bottom now a little bit. I'm starting to get a little bit of a special interaction here. And that bond will rotate until the bond will rotate until, I need a different color here. I only have, unfortunately, my palette, I only have a few colors. That bond will now rotate. How do I do this? Rotate this direction in order to put that carbon-silicon bond at the very bottom. So if the proton adds from the top, the carbon-silicon will then spin around to the bottom because it's already a little bit at the bottom. And you'll end up with the H. You'll end up with this H in the same place where that silicon used to be. And so the substitution of the silicon will be stereospecific. It's not interesting in this case because you don't generate a stereoisomer. So this is, I'm not trying to show arrow pushing with my dashed arrow. I'm just saying there's stabilization there. So then the silicon would get popped off through a full, through a two-step mechanism. I'm not going to draw that two-step mechanism for substituting off the silicon. But again, in a vinylsilane, the carbon-silicon bond is not souping up the alkene. It doesn't make it more nucleophilic. It's not until you add the electrophile that the silicon can have even partial alignment with that developing carbenium ion. So allylsilanes are more reactive than vinylsilanes. Okay, so let's take I don't know if this is a subtle example, but it's an interesting example. So you should have learned about a reaction called the Friedel-Crafts acylation reaction when you took an introductory course in organic chemistry. And what is a Friedel-Crafts reaction? You take some sort of an acyl chloride, usually, in rare cases anhydrides, but acyl chlorides are the most common substrates, and we add a Lewis acid in there. And the most common Lewis acid that we're introduced to is aluminum trichloride. Now, when I see this oxygen atom, right, everything in me wants to take that lone pair on oxygen and add to the aluminum. I promise you that's happening in the reaction. I also promise you that if you do that, you're going to have to go right back to where you started because you can't get to a productive pathway by donating the lone pairs of the oxygen into the aluminum. Yes, it's happening, but you're not going to be able to explain the products by doing that. So after you've done some mechanisms for Friedel-Crafts alkylations, you'll know right off the bat, okay, eventually I have to use the chlorine lone pairs to add to the aluminum. And so let's go ahead and do that. So when we, I'll draw the mechanism down below. The question here, when you do Friedel-Crafts acylation or Friedel-Crafts alkylation or nitration or sulfonation is, what kind of substitution pattern do you get? Are you going to add ortho to the substituent? Are you going to add meta to the substituent? Or are you going to add para to the substituent? Now, we've got this carbon-silicon substituent on here, and what's the effect going to be if you have silicon on a benzene ring? So you should have memorized already what happens if you have a nitro group on a benzene ring. Is that an ortho-para director? What happens if you have a methoxy group on a benzene ring? Is that an ortho-para director? Well, in this case, you can see it doesn't add ortho, doesn't add meta, doesn't add para. It replaces the silicon, and we call this Ipso substitution. Not ortho, not meta, not para, Ipso. It replaces the group that was there originally. So silicon will do this, tin will do this, boronate minus will do this. All the things we use for palladium catalyzed reactions lead to replacement of the group that was originally there. So this is a Friedel-Crafts reaction where we get Ipso substitution. And let's go ahead and talk about the mechanism for this and the interesting selectivity that you see because you couldn't have predicted what would happen here. And what is it that's hard to predict? What's hard to predict here is that there are two spots where electrophiles want to add. The arene ring, the benzene ring, and the alkene. both of those are going to lead to beta-silocarbenium ions. And so which one is more reactive? You couldn't know that. I have to show you that. Let's go ahead and walk through the mechanism. So again, don't use the oxygen lone pairs to coordinate to the Lewis acid, the aluminum here. Yes, we all agree that's happening, but it just doesn't lead to a productive reaction pathway. So eventually, we're going to coordinate the chlorine lone pairs, and we generate at the same time this chloronium species and an aluminate species. And there's a lone pair over here, anti to that carbon-chlorine bond, that weakened carbon-chlorine bond. Look at that bond there. It's so weak. And there's a lone pair anti-paraplanar to that. It's not like it starts to donate. It was already donating into that carbon-chlorine bond. You can't stop it from being aligned with that carbon-chlorine bond. Now it just pushes out that leaving group and generates an acylium ion. Look at that acylium ion right there. It may look lousy because it has O+, but it's got filled octets for all the second row atoms. That's better than a T-butyl carbocation, that acylium ion. So it may look weird to see O+, but don't get freaked out by that. It's still a great electrophile. It doesn't want to have that O+ on there. And so the question is, what's more reactive? Do we want to disrupt aromaticity, or do we want to use this alkene in order to make a beta-silocarbocation? What happens if you use the alkene? What happens if we use, remember, you substitute on a vinylsilane, you substitute next to the silicon. You substitute next to the silicon. So when we draw this arrow pushing reaction, and we add that vinylsilane here to this acylium ion, now we end up with this beta-silocarbocation. There we go. And somewhere around here we'll have some sort of a nucleophile that can now do a two-step substitution process. And I'm not going to show both the steps, but you make a siliconate. So you do get substitution on the vinylsilane, but that's the minor product in this reaction. It represents only 5% of the product mixture. If you thought that the alkene, the vinylsilane part, would be more reactive, well, you're close. I mean, it does generate product. That's some of the product in this reaction. The major product in this reaction, you couldn't have predicted which was more reactive. This is why I have to tell you that the simple benzene ring, the phenyl group, attacks at a slightly faster rate. In fact, I can tell you how much faster it adds. Right? How would I tell you how much faster it adds? You get 70% of this product, 5% of that product. 70-to-5 ratio. I'm not good at 14-to-1 ratio, right? One of those, the attack of the benzene ring attacks 14 times faster than the vinyl group attacks. And you can convert 14 into a kcals per mole. How many factors of 10 is 14? It's like 10 and 4, or 10 plus 4, it's somewhere between, I'm not good with the math. It's more than 1.4 kcals per mole in energy. One transition state is more than 1.4 kcals per mole in energy lower. Yes?
Is that because the carbocation that you form is just much more stable compared to attaching to all of them?
That's part of it, yeah. So let me just keep going here. So look at this. We generate this beta-silocarbocation that's also allylic. It's also stabilized by the diene. And I can draw another resonance structure for this, where the other resonance structure puts the carbenium ion also beta-silo. Boy, that is a great-looking beta-silocarbocation. It's allylic, it's beta-silo on both ends. It's like, what could be... The problem is we had to give up aromaticity to get there. So you couldn't have predicted the cost of how much... Right? Yeah, it's lousy to give up aromaticity, even if you can make this great beta-silocarbocation. Turns out that the Ipso substitution is the favorable process here. This is an unusual case. You would almost, in modern organic synthesis, you would almost never have an extra vinyl group sitting around. It would just be a trimethylsilo would be the typical substituent. So there's only, if it's trimethylsilo, the only place you can add is here. Okay, so vinylsilanes or arylsilanes, you add next to the silicon group because you want to make a beta-silocarbocation. And they're not as good as allylsilanes. Allylsilanes are more reactive. All right, so we've talked about tri-substituted olefins. We talked about allylsilanes, allylstananes, allylboronates, just making CC double bonds more reactive. And when I started off this lecture, I talked about how amazing that oxidosqualene cyclase enzyme is at synthesizing steroid skeletons. Like, how magical is that? But you know what? Once you know all these tricks, tri-substituted olefins, put in some Lewis acid, makes an oxocarbenium ion. There's nothing that enzyme is doing that is special in any way. You can just go into the lab and then synthesize a long chain like this one. And if you put an initiator on one end, notice they're just putting in some stannic tetrachloride here. And so all they're doing is they're just using the same tricks that we use. It starts off with addition to the Lewis acid to make this stannate species over here. So here you end up with stannate next to an oxonium. And now these lone pairs are just waiting to push out that lone pair. And that makes this electrophilic oxonium species. And now we are set up 6 atoms away. You can do that just like the enzyme can do it. Makes the ring just like the enzyme makes it. This bond will swing over. Is this all happening? I'm going to draw this in dashed bonds because I don't want to imply that this is all happening in a concerted fashion. But if you design your substrate right, you'll end up being able to do this tetracyclization to make 1, 2, 3, 4, 5, 6 stereogenic centers, 4 rings, just like the enzyme does. You know, the yield is 30%. You get some other cation reactions occurring. Sometimes the last ring doesn't form and you get elimination, but that's a pretty good yield for a one-step tetracyclization to make all those stereogenic centers. And unlike the enzyme, which ends up with these methyl groups in the wrong places that have to get burned off enzymatically, this process doesn't put methyl groups where you don't want them. So notice that this middle double bond is not a tri-substituted olefin, and you still get a 30% yield out of this process. What's the last step out of here? Well, unfortunately, the last step is to pull a proton off, right? You pull the proton off, and you don't get great control out of that, right? You get most of the double bond ends up here, but you would also end up with double bond isomers at other positions and things like that. You know, how could you control that? Well, you would have used an allylsilane, and then you'd know exactly where the double bond was going to end up. Yeah?
How come you're not saying that it's concerted? Because I was thinking that you have stereo, like the stereochemistry is specific, right? Like it's pulling up the desired product. And if it was not concerted,
Yeah, you can. Even if it's stepwise, you can still get. Each ring. Let me just make sure I get this drawn in here correctly. Yeah, so each ring can form. So once you form a carbocation here, the next ring can form stereoselectively. I'll just put OR here. The next ring can form stereoselectively even if it's not concerted. So attack through a chair-like transition state because it prefers chair-like transition states. Very hard to know is whether all those bonds are forming concerted or not. If you add to the bottom face, so there's 2 faces to this pi bond. I'll get to your question in a second. So again, we're talking about why. How do you know, why doesn't that have to be concerted? Well, you can also be stereoselective if it's not concerted. There's 2 faces to this pi bond right here, and if you add from the bottom face, you have to go through a boat-like transition state, and that's about 6 kcals per mole higher in energy. So whatever, factors of 10, that's slower. That's way slower, 10 to the 4th slower. Yeah.
How much slower is this than like an enzyme? Because I would imagine like the enzyme forces the molecule into like the configuration, but I would imagine like if you're doing this in a beaker, then you have to sort of like wait for the molecule to kind of like naturally get to that conformation.
Yeah. So the question is this really faster than an enzyme? Aren't enzymes way faster? You know, if you take a course in enzymology, some of the things that you learn about is that you have to get, well, this is not really enzymology. One of the challenges here is that you have to get the substrate soluble in water in order to use enzymes. These types of substrates are not easily soluble in water. And the big advantage of organic chemistry, whether you're making industrial polymers like polymethyl methacrylate or vinyl chloride, is you can take super high concentrations, pure monomer, add in one tiny bit of catalyst, and boom, instantaneously make tons, kilotons of material. And you can't do that with enzymes. You have to keep the concentrations reasonable, and it almost always needs to be, not always, but usually is an aqueous solution for enzymes. So when it comes to practically making tons and tons of material, you cannot beat organic synthesis. There's no enzymatic process that can make, plastic bottles or the polymers in this tables at the same rates. Nothing can touch enzymes, Ziegler-Natta catalysis, the radical polymerizations that we do industrially, for pure rates. And a lot of that has to do with concentration. We can use high concentrations in organic chemistry. What enzymes are usually great at is selectivity. Like, what if you wanted to have this proton over here down? Not so easy, right? Right, the natural enzyme only gives you one stereochemistry, but sometimes you can fiddle around with enzyme active sites and change that. But in this case, you're going to get what the substrate tells you you're going to get. It's going to fold up into chairs and cyclize through chair-like transition states, and that you can't easily change. An enzyme could force it to go through a boat. I'm not saying you can easily design that, but okay. Boy, double bonds attacking carbonyl groups. That's the stuff we've been talking about. And we talked about allylsilanes and allylboronates, and I don't know if we talked about allylstananes, but you know what we kind of skipped? We kind of skipped talking about lone pairs, right? Why are we talking about carbon tin bonds and carbon silicon bonds, but we skip talking about lone pairs on O-, on OH, on OR, and on nitrogen? Aren't those lone pairs supposed to be way better than bonds at donating into things? And the answer is yes, some lone pairs and most lone pairs. So let's step backwards a bit and talk about double bonds that are souped up not by long bonds, but just by lone pairs next door. These lone pairs right here are going to donate into pi star and generate a new pi-like orbital that is very nucleophilic on that end carbon. And if you look at the HOMO, the highest occupied molecular orbital for this, you would see that that HOMO is biggest over here on this carbon atom. Not on oxygen, not on this carbon, but it's biggest over here. And that doesn't look like a big difference in the shape of the HOMO, but the relative size difference here versus here makes all the difference in the world. There's no question about where you're going to be forming the bond because the HOMO is bigger here. Now I've overlaid this picture of the HOMO with this kind of net-like drawing that shows you a picture of charge distribution. You know, charge also plays a role in organic reactions. And when you look at where is the negative red charge on these types of molecules like an enol ether, it's mostly associated with oxygen. What we're going to find is that when you do reactions that are mostly controlled by charge, like protonation, you get faster reactions on oxygen. You protonate faster on oxygen. If you're trying to make carbon-carbon bonds, you react faster on carbon. That's the general rule that we're going to see. Okay, so again, lone pairs. How did we miss that? We went straight to allylsilanes and tricky stuff like that, and we seem to have skipped lone pairs, souping up double bonds. So where do you get these types of enol ether species from? Well, tautomerization is the simplest way to get access to an enol, to an alkene that has a lone pair next door, and that's happening whether you want it to or not. So if you just take acetone and you put it in some sort of a solution, you will have an equilibrium amount of the enol form. So this is the keto form over here. So this is the keto tautomer. Tautomer means you've picked up a proton and moved it somewhere else. That's a tautomer. And this is the enol form. Keto form and enol form. And you know, the keto form's favored. It's got the carbonyl group. CO double bonds are favorable. You can't control the equilibrium here. The equilibrium will favor the carbonyl side. Let's go ahead and talk about the mechanism. It is always a two-step mechanism to enolize. Doesn't matter whether you're using catalytic acid or catalytic base. They both accelerate the reaction. Let's go ahead and talk about the acid-catalyzed enolization process first. So if you have a catalytic acid, it's so easy to enolize. Even in neutral water, there's enough hydronium ion in there to act as a catalytic acid, or other molecules in there. So let's go ahead and draw out. So the mechanism is protonate first, right? Deprotonate second. That's pretty easy. It's acid conditioned, so we're saying it's acid catalyzed, so protonate first. Let's go ahead and draw out that oxonium ion intermediate. And now because it's got that O+, it's easier to deprotonate. So I'll go ahead and draw my conjugate base there. And draw the lone pairs on that A-. And now we just pick off the proton. There we go. 2 steps. Always 2 steps. It is never 1 step. It is not possible to enolize through a 1-step process. So you may be tempted to say, hey, wait a second. Right? Why don't I just get really fast here and do it like this? I don't want to use regular arrows here because no, not ever can it do that. I hope we're going to start talking about paracyclic reactions at some point coming up. That process that we just drew right there violates a fundamental principle of orbital symmetry. It is impossible to do that in a concerted fashion through a paracyclic reaction as a one-step process. Simple alkenes can't do that. If you just take a long alkene like this, the H's don't shift around and tautomerize. There's no one-step process for doing that is plausible. So tautomerization, or if you somehow had to move this H to the other end of the double bond, that's not a one-step process ever. So, okay, so what about base catalyzed tautomerization? So if you threw a base in, what can you make catalyze accelerate the rate at which you form enol by putting a base into the reaction? And the answer is absolutely yes. Of course you can have bases accelerate the rate of keto-enol tautomerization. So it's basic, so tautomerize first to make an enolate like this, and then we end up with the conjugate acid there. I don't know, let me draw that in a nice high contrast black here. Like this, and then we draw our conjugate acid. If I drew B as neutral, I better put a positive charge there. And then in the second step, you know what? Who cares about the second step? Nobody in the world cares about enols if you have enolates floating around in your solution. You know, if you're starting to think about the nucleophilicity of enols at this position, just stop it, because once you generate an enolate, that's going to do all the work in your reaction. So base catalyzed tautomerization to form enols is not important. Once you form enolates, it's going to be this that's doing all the nucleophilic attack in your reaction. So this is not really important under basic conditions. It's the enolate that's important. So again, if you have an enolate, if you've generated even a tiny amount of enolate, even if there's a lot more enol present, right, this is going to be doing all the nucleophilic attack to make carbon-carbon bonds or add to other stuff. So we don't usually talk about catalytic catalysis of enolization by bases. We usually talk about forming enolates under basic conditions. Okay, I'm going to stop right there. When we come back, we're going to talk more about enols, enol ethers, enolates, enamines, nucleophilic pi bonds, and it's another powerful way to make carbon-carbon bonds.